Welcome back to Calculus 2. This video is section 1.5 on substitution. We'll begin by looking at the notion of a change of variables. So change of variables. Let's suppose that we have a circle centered at a, 0. It's given by this equation. We'd like to move the center from an arbitrary location, a, 0, to the origin. That can easily be done if we take this x minus a and term it as a new variable, x tilde. Then doing so, the equation becomes x tilde quantity squared plus y squared equals r squared. An equation for a circle centered at the origin. Under the change of variables, the pink circle moves to the orange circle. Okay. So that notion is carried over into indefinite integrals, or definite integrals, we'll see later on, through the notion of substitution, a change of variables. Let's take a look. So through change of variables, we can go from something that looks rather complicated to something which is actually, under the change of variables, an elementary integral, for which we know an antiderivative. And thanks to changing back to the original variable, can produce an antiderivative for the original integral. Okay, so what's required? Well, we make a definition of a new variable u as a function of the old variable x. We require that that function g has a derivative which is continuous on an interval, and that the function f be continuous over the range of g. All right, so we're going to want to rephrase our complicated looking integral into an elementary integral. So we'll want to have an antiderivative for the integrand little f, and then this computation will go through. All right, let's walk through the arguments why these equalities hold. And to do that, we'll need, first, the chain rule. So remember that the chain rule is the method of differentiating a composition function. The outer function differentiated, evaluated at the inner function, product, the derivative of the inner function. Now, here's the substitution statement. And to get started, let's apply the chain rule. Let's apply the chain rule to this antiderivative, capital F, at g. So that's a composition. The derivative of the outside function evaluated at the inside function times the derivative of the inside function. Next, let's take advantage of capital F being an antiderivative. Do a quick recall on what it means to be an antiderivative. Capital F is an antiderivative of little f if you differentiate the capital F and recover the little f. In our substitution statement, we have that capital F is an antiderivative of little f. Thus, in this chain rule computation, if we see capital F prime, we can swap out capital F prime with little f. Let's go ahead and do that. Capital F prime is little f. So now we have a restatement of our chain rule computation. So far, so good. Let's integrate on both sides. We're going to integrate with respect to x. Let's look at the right-hand side first. Throwing an integral symbol and the differential produces a new right-hand side. On the left-hand side, we have that we're integrating a derivative of a function. So do we know an antiderivative for this quantity? Well, of course. If we differentiate this expression, f composed with g plus c, we'll get exactly this integrand. Very good. Now, let's introduce a new variable, u, for this quantity g. Then the left-hand side will become capital F at u plus c. And then the idea is that we want to change away from original variable x to a new variable u. So looking on the right-hand side, we know what to do with g of x, becomes u. But we're going to have to figure out what to do with this differential dx. So we take our original identification of u being g and compute the differential of du. So that's going to require taking a derivative of g with respect to x and tacking on the differential dx. Therefore, g prime of x dx becomes du. Excellent. And that establishes this substitution rule. That through this step of changing variables by introducing a u, we can evaluate a complicated looking integral. Let's do an example. So here we have the integral of a base raised to a power. We could expand that out if we wanted to, but this power of 99 is rather dissuasive. Instead, we can use this method of substitution by setting the base equal to a new variable u. And then we're going to have to figure out what happens with the differential dx. Well, if we look at the differential du, differentiating 1 minus x, that produces a minus 1. Place that on to dx. And then it's going to be a little bit more convenient to solve this equation, solve that for dx, and get that dx is negative du. Good? So again, we're going to swap out 1 minus x with the new variable u. And then on the differential dx, we're going to swap that out with negative du. Let's go ahead and do that. So here's the original integral. And then thanks to the change of variables, here's a new integral written out in the variable u. And this is an elementary integral, which we know how to evaluate. So we go ahead and we do that. We increment the power 99 to 100 and divide by that new power. This is an indefinite integral, so we pick up a constant of integration. Fantastic. Now, the original integral is given as an expression in x. Therefore, we want our antiderivative to also be a function of x. And that's simple enough. All we have to do is swap out our u, which was defined as 1 minus x, and come up with our final answer. Beautiful. So here's an assignment for you. Essentially the example that we did, but the integrand has one more factor of x. So play around with that, see how that introduction of the factor x changes the substitution. Very nice. Okay. Let's do a little bit more on looking at from indefinite integrals to definite integrals. And let's spend a little bit of time thinking back on composition. So the composition of two functions. Here we have a picture, 3 number lines. And we're starting with an input x. And under a function g, that value x is transformed into a new value, g of x. But g of x is just a number, some point on the number line. And then suppose that it's a point in a separate function, f. Then we can watch f transport that value g of x to a new value. So this means that we're evaluating f at the input g of x, hence this notation. We can simplify that idea by instead referring to this value g of x as u. Then the output of u under f would be the value f at g of x. So now is where we can take advantage of the notation of composition to say that, well, if we started at x and wanted to produce this value f at g of x, that would be done by this function termed f compose g. So f compose g at x would be the same as f at g of x. Therefore, we can write down that f of u is f compose g of x. Good. So we've done substitution for indefinite integrals. We now want to do substitution for definite integrals, and definite integrals have bounds. So taking x to be the given variable of integration, x will have some upper bound, b. And in substitution, we reterm our integral as with integrand f of u, so that new variable u would have as upper bound g of b. If we're given a lower bound on x as a, then the lower bound on the new variable u would be g of a. Okay, very nice. So let's look at substitution in definite integrals. So here's the statement of substitution for indefinite integrals. In other words, if we have some indefinite integral and we're able to find an antiderivative, then rewriting that as a definite integral, knowing an antiderivative, we simply evaluate the antiderivative at the upper and lower bounds and take the difference. So doing that, this is just notation. Come up with this expression. But as this is a composition, we can rephrase this as the antiderivative, capital F, at u, where u is taken between lower bound g of a and upper bound g of b. And then this expression we can express out as a definite integral for little f integrated with respect to u, where u is traveling between g of a and g of b. Very good. So let's employ substitution in a definite integral. Okay, focus in on the integrand, and maybe it seems like a complicated integrand. But looking at the power on the exponential, we have a degree 2. And then looking at the polynomial, 2x plus 1, that is degree 1, one less than the exponent. All right. So this one is set up nicely such that if we take the exponent to be a new variable, u, that when we compute the differential of this new variable, we'll have to differentiate the x squared to get 2x, differentiate the x to produce 1, differentiate the negative 1, it goes away to 0, so that the differential du is 2x plus 1 binomial multiplying dx, which we can exactly match up. So that's going to work nicely. But this is a definite integral, so let's pay attention to what happens with the bounds. So the bounds will be bounds for u, and we simply have to plug in x equaling negative 1, get positive 1, minus 1, minus 1, or comes back to minus 1. How about the upper bound for u? Well, that's going to correspond with the upper bound for x, which is 1. Then having 1 plus 1 minus 1 gives you 1. So the bounds on x happen to be exactly the bounds on u. But through this substitution, we're able to rewrite what seems like a complicated integral as a very elementary integral. Good. And then, since e is its own derivative, we can plug in at the upper bound and subtract away the antiderivative e at the lower bound. And since a definite integral is a value, we are done. No need to swap back to the original variable. No, we're looking for a value. Perfect. Let's do another example. Here we're using a nice notation, letting capital I represent the entire integral. Focus in on the integrand. It's a rational function. The denominator is degree 4, the numerator is degree 3. And when you differentiate the denominator, 4x cubed, 6x, 0, you see that the derivative of the denominator is twice the numerator. Very nice. So here we are. Set u equal to the denominator. Get that the differential du is twice the numerator, dx. And then for bounds, the original bounds on x are 0 and 2. If you plug in the lower bound to this definition of u, we get 1 as the lower bound for u. And when you plug in 2 to this definition of u, you should compute out u has an upper bound of 41. Let's make that change and take advantage of our nice notation, capital I. So capital I then is denominator u. Numerator, we've got 2x cubed plus 3x. We'll have to multiply that by 2 in order to produce the differential du. Hence, we're going to have to compensate with a multiplicative 1/2. The original bounds on x were 0 to 2, but thanks to this definition of u has bounds 1 and 41. Looking at the original I, it's a complicated integrand, but thanks to the substitution of u, we have an elementary integral. So this will evaluate to the natural log of the absolute of u. These absolute values are superfluous in this case because the bounds are positive. And when we plug in the lower bound of 1, we know that the natural log of 1 goes to 0. Thus, our answer is 1/2 ln of 41. Perfect. So here's an assignment. Implement u substitution to evaluate this definite integral. Make sure that you change your bounds. Here's another one, a little bit more high level. In the previous video, we talked about these properties for integrating even and odd functions. When you have symmetric bounds of integration, -a to a, use the change of variables to formally establish these identities. Good. Here's another nice assignment. So if you have a semicircle with radius 1, verify that it encloses an area of pi/2 square units. Follow steps 1 through 3 to establish this fact. Nice. That brings us to the end of the video. Thanks so much for watching. See you on the next one.